Warm greetings, everyone. I pay my regards to the European Structural Integrity Society to have organized the 7th International Conference on Crack Path 2021. My presentation is on a review of application of data science tools in crack identification and localization. This review paper is authored by Nabam Teyi and Sandeep Singh, both from Northeastern Regional Institute of Science and Technology, India. I am Nabam Teyi. Currently, I am teaching mechanical engineering courses at my institute. The motivation for me to take this review is primarily because I am pursuing my PhD on model-based identification and localization of transverse crack in spinning rotor. I had to undertake extensive survey of literature in the area of structural cracks to arrive at my set objectives. This presentation presents a section of my survey which is focused on literatures on cracks in shafts and cracks in beams, which use certain data science tools, artificial intelligence techniques, and machine learning models in crack identification and localization. I have used search engines like Google Scholar and my institute's journal subscription database to collect a horde of relevant literatures. From the list, I have chosen 28 significant fitting research papers for this presentation. Although there are a few exhaustive review articles published in the same line, like C et al. Last year published a review article titled Potential Difference Methods for Measuring Crack Growth, a review in the International Journal of Fatigue, and Nasri et al. Published an article titled Fracture Mechanics and Mechanical Fault Detection by Different Methods of Artificial Intelligence, a review in the journal Engineering Failure Analysis. I still hope my presentation and subsequent publication provides a good note of reference for other scholars. Let's begin. What is a crack in shaft? A crack is a small opening like a slit cut on the shaft surface which may occur due to poor manufacturing of the shaft material or which occurs during the operating period of the component. Such cracks are so small that it is impossible to detect their presence visually even when the shaft is freshly manufactured. Cracks are definitely impossible to be detected when the shaft is rotating. Therefore, for crack identification for its presence, crack localization for its location, and crack assessment for its depth and severity, need modeling and analysis using various techniques to be validated experimentally or vice versa. The models may have a single crack or a double crack or multiple cracks, and the cracks could be longitudinal, that is, the crack direction is parallel to the axis of the shaft, could be slant, that is, the crack appears at an angle to the shaft axis, or could be transverse, that is, it is perpendicular to the shaft axis. Transverse cracks are the most common and the most serious. Many authors have used artificial neural network in their shaft crack analysis. Artificial neural networks are networks of artificial neurons that can communicate with one another. As learning continues, the weight of neurons and edges varies. Uh, Saridakis et al. In 2008 considered the dynamic behavior of a shaft with two transverse cracks characterized by three measures, that is, position, depth, and relative angle. The evolutionary algorithm and neural networks both assist in reducing calculation time while maintaining accuracy. According to the findings, the proposed method can be utilized to swiftly detect cracks. A few authors have used genetic algorithm in their analysis. A genetic algorithm is a search heuristic based on Charles Darwin's natural selection hypothesis. You can see in the algorithm, it initializes the population randomness and then uh, fitness function with fitness approach is calculated. If the optimum solution is found, then the algorithm is terminated. Otherwise, there is mutation, selection, and crossover happening to further check for the fitness function with fitness approach, and the optimum solution is checked as well. So this cycle continues until the criteria is reached. Hay et al. In 2001 described a shaft crack detection approach based on genetic algorithms which structure the shaft crack detection problem as an optimization problem using the finite element method. Um, Then there's a tool called continuous wavelet transform or discrete wavelet transform. A function is decomposed into sine and cosine components using the Fourier transform, the fast Fourier transform FFT. To break down that function into wavelets, the continuous wavelet transform is utilized, that's CWT. The discrete wavelet transform, DWT, separates a signal into sets. Here are a few authors who have used CWT and DWT in their crack analysis. Babu and Sekhar in 2010 performed soft crack identification using artificial neural network and wavelet transform data of a transient rotor. The CWT plots were used to locate cracks with one-third and half crucial peaks serving as crack indicators. The crack parameters were calculated using the amplitudes of subcritical and critical peaks from the CWT plots as input to the neural network. Some notable mentions, meaning a few authors have used some really unique tools for their crack analysis, like Xiang et al. In 2008 used B-spline wavelet on the interval tool. Mm, uh, the proposed method was capable of detecting cracks in a shaft with high accuracy. However, in order to use this method to detect a crack in a running shaft, more research is needed. Muhammad et al. In 2014 used peak position component method in their shaft crack analysis. Bukapatnam et al. In 2018 used self-adaptive entropy wavelet technique. Radial-based function-based support vector machine was used to get a classification accuracy of 99.3%. As a result, the proposed method should be developed in the future to investigate the problem diagnosis capabilities of other rotating components in industrial rotating machinery. Auta et al. Last year used artificial immunosystem AIS for structural hand monitoring of cracked shafts. Very quickly, we'll see what is a crack in beams. Due to an increase in shear stress, the cracks in beams form near a support, such as column or wall. Because they are slanted 45 degrees from the horizontal, these cracks are referred to as shear cracks. Here is an example. Here are illustrations of cracks. You see a single crack model, you see a multiple crack model, you see a double crack model, and then you see amplifier and analyzer put in the crack beam, and these are used to record the vibration of the beam in action. Here as well, in crack beam analysis, ANN is being used, like Sahin and Seno in 2003. Sahin and Seno in 2003 again have used ANN in two of their publications. Vakil Bagmi says et al. Use GA in the crack beam analysis. GA means genetic algorithm. Particle swarm optimization. PSO suffers a population of potential solutions throughout the search space using a simple mathematical formula based on particles' position and velocity. Mohan et al. Using GA and PSO, a comparison study was conducted on fracture detection on beam and truss construction based on changes in natural frequency. For many types of construction, the performance of PSO in locating and quantifying the fracture was far superior than that of GA. Then the Adaptive Neuro Fuzzy Inference System, ANFIS, was created by Zhang in the 90s. It translates input characteristics into input membership functions into a set of if-then rules, rules into a set of output characteristics, and output characteristics into output membership function, and finally output membership function into a single value output or decision associated with the output, as you can see in the picture. Nanda et al. Use ANFIS in their analysis. Then there's evolutionary algorithm. It was developed by Furukawa and Yagawa in 1997. The reproductive operations of continuous evolutionary algorithm are intended to be similar to those of genetic algorithm, as it takes advantage of probabilistic features in GAs. As you can see in the picture, the algorithm is very similar to genetic algorithm. Shim and So in 2002, 2003 uh, have used entries and CEA in their approach. Shim and So again used in 2002 as well, the entries and CEA in their approach. Machine learning models. Machine learning models are essentially trained algorithms that are created when algorithms apply to a certain data collection. You see in the picture, first the data are collected, then the models are trained with those collected data, then the models are evaluated, and finally the models are used for the requirement. Uh, Decision tree is one such machine learning model. A decision tree is a diagram or chart that aids in the decision making process or displays statistical probabilities. Random forest is an ensemble of many decision trees. So it's many decision trees make up a random forest algorithm. So Chaudhary et al. In 2020 use both DT and RF in their crack beam analysis. The outcomes of the connection were beam natural frequencies, which were used as the input value for irrigation algorithms. When compared to the DT aggressor, the RF aggressor predicted the parameters with more accuracy. That is their finding, Chaudhary et al. In 2020. Support vector machine. Support vector machine divides the data into classes by drawing a line or a hyperplane. As you can see in the picture, the data is divided into class 1 or class 2. Liu and Meng in 2005 used this support vector machine in their crack beam analysis. The performance of crack detection using neural networks and support vector machines based on natural frequencies were compared in a study. Crack position and depth might be estimated with a minor size inaccuracy as it was discovered. The results demonstrated that the support vector machine was a powerful and effective fracture detection approach. Then there's LASSO, least absolute shrinkage and selection operator. It's another kind of machine learning tool. Chaudhary et al. Used LASSO. LASSO and regression analysis were considered, with LASSO focusing on feature selection and regularization, and ridge addressing collinearity difficulties. Ridge analysis outperformed LASSO analysis in terms of accuracy. The theoretical results were compared to the experimental data at the end, yielding an error of roughly 4%. Then Behra et al. In 2019 combined too many artificial intelligence tools as hybrid AIs. They combine fuzzy logic, genetic algorithm, and rule-based techniques. And the hybrid methodology was used to overcome the limitations of single artificial intelligence system. When the output findings for fracture location and crack depth compared to experimental data, the variance was found to be within the acceptable limits. Hence, I have reached to my conclusion. It says wavelet analysis and finite element analysis were utilized to derive the structure's vibration indices, which are natural frequencies and mode shapes, which were then used to detect fractures. The fuzzy logic approach was utilized to develop fuzzy controllers using vibration inputs from operational machines and structures. Many authors use adaptive neurofuzzy inference system ANFIS and neurofuzzy and evolutionary algorithms like CEAs and MOP CEAs to detect beam structural faults. Time taken to find problems using genetic algorithms were measured in milliseconds. Particle swarm optimization, genetic algorithm fuzzy, genetic algorithm neural, and genetic algorithm fuzzy neural networks examples of hybrid algorithm for structural health monitoring. Special technologies such as B-spline wavelet on the interval, that is BSWI, peak position component method, that is PPCM, self-adaptive entropy wavelets, that is ACW, and artificial immune system AIS were employed for crack analysis. With this, I'm done with my presentation, and here are my 28 references. Thank you very much. Thank you very much. Thank you all.